Hi everyone, welcome to the fourth workshop of Hacked of Tomorrow. This workshop will be focused on the blockchain technology and leading by Rohan Sharan. And the topic of this workshop is understanding BSV blockchain and SP wallet. The BSV blockchain is also the main sponsor of the Tech of Tomorrow conference and Hack of Tomorrow, which will be this weekend, 22 and 23rd of March in the Franklin Templeton. Together with us is also Michał Pawełski, who is the co-founder and CTO of 4Chain Studio, which is a supplier in BSV ecosystem, deliver the knowledge and tech skills for BSV blockchain for our customers and also for the enterprise. So, guys, Rohan, I want to give you the stage and let's start.
All right. Good afternoon, everyone. I'm Rohan Sharan, the Developer Relations Associate at BSV Blockchain. Today's workshop, it will be 1.5 hours long. Try to stick till the end and focus so that what I impart the knowledge to you today would be helping you build any blockchain application on the most powerful blockchain out there, which is the BSV blockchain. So let's get started. First of all, why should you care about blockchain? From your perspective, there are tremendous job opportunities out there for blockchain engineers, which is going to give you an edge over just any full stack developer for good job opportunities. It's going to not only do that, but also give you a depth of understanding, even if you just try to develop into a normal backend developer. It's going to give you skills in understanding network theory and cryptography at a deeper level, which will help you, even if you're not building a blockchain application. And blockchain is the future of finance, security, and distributed applications. So it's going to help you if you have any ideas to build your own application or startup in the blockchain space. So stick around and we'll master blockchain together. So the goal of today's workshop is for you to understand the fundamentals of blockchain from scratch, even if you are a total beginner having no knowledge of blockchain. We'll cover it succinctly and you will learn about the use cases where blockchain applies the strongest, which will help you get ideas of which applications to build in the current hackathon that will begin. Blockchain applications require wallets which hold digital assets. So creating wallets for your users becomes quite important. And then creating transactions with those wallets between user to user. So that's what we are going to learn at the end of today's workshop and at the beginning of the next workshop, which we'll be having tomorrow, where we'll be deep diving into the code of how you can develop your own application. You'll get a template of doing that also tomorrow. So let's get started with today's workshop. Why blockchain as a technology? Why is it having such an impact that it's making a difference to get used and a lot of hype around it also? That's what we're going to understand first and foremost. To understand that, you need to understand what are the layers of the internet. To appreciate where blockchain is coming in as another layer of the internet. So what are the layers of the internet? Well, the internet layers are divided into 7 as such, which are the OSI layer stack, protocol stack of the internet. I'm showing you here the 5 most important layers, which makes up the protocol stack that gets used. It's starting from the actual C cables that link computers, the physical cables. That's the physical layer of the internet. Then comes the link layer of the internet that structures the data frames that gets transmitted through the packets in the physical layer, in the deep sea cables. And then we have the network layer, which transports data which is made up by the TCP protocol predominantly, and then we have the application layer where you as developers build applications, right? Now what's happening is we are having a gap in the stack of a true data economy to be forming on the internet. The economic layer of the internet protocol stack has been missing. And for wanting an extreme data economy, that's the future as we are stepping into more and more IoT devices, capturing a lot of data, and also AI agents uh, transmitting, exchanging data at a larger scale automatically. It naturally brings in the demand for a global data economy to be forming in a more formalized and a highly hyperscaled model. For that, there was an error code also that was never completed as part of the HTTP protocol suite, which makes up the current request and response cycles of every web application, which is that if a user requests a website for data, and if the website address is not present, many of you who are developers would be familiar, you would get a response of 404, error 404 standing for no file present at that URL, right? Now, another code exists, which is 402, which was for reserved for future use, which was never used because the solution of micropayments wasn't there on the internet at that time. And that's what brings us to the focus of the global data economy, which we're talking about, that a server, if it does not receive a payment with the request that's coming in, would respond with the error 402, that payment is not found. And that's going to complete the cycle of the protocol stacks. And finally, you having a stack, a protocol to follow for your web applications for transmitting not only data, but anything of value, any object of value. It can be digital or physical, ownership of any object to be transferred along with the data between computers. That is what was the purpose and the idea of micropayments on the internet for the data economy. And it's there in the name itself. Bitcoin, as it was launched, the first application of blockchain, bit stands for the unit of data, as you all know it. Megabits, gigabits, that's the speed, how we measure even per second, is how we measure the data network speed that you get on your devices. And data that is monetizable, that's monetized with payments, is the purpose of why Bitcoin was launched. Data is the new oil is another thing you would have heard in many machine learning circles, where data is more important because that's what is used to train many models and even to develop statistical applications that all require data. So when Bitcoin was launched as a white paper in 2009, it was launched with the title Peer-to-Peer Digital Cash System. Now, every term here is important. Just like your email servers, which are peer-to-peer, your emails are following a protocol, another protocol, which is the SMTP protocol. It's a peer-to-peer protocol where you can transport email messages between servers to servers. That's exactly what the idea here is, to achieve another protocol where you can set up your own server and another person can have their own server, and both of you transmit not only just messages, but bitcoins in this case, and anything of value in the generalized case. In the first section of the white paper itself, what you see on your screen right now is the first section of the white paper. It talks about how commerce on the internet had come to rely on credit cards and traditional financial institutions with many multiple middlemen that increase the cost of transactions and increase the minimum practical size of transactions also. And that's making micropayments not feasible. By micropayments, we mean payments less than $1 in size, and that too transmitted between countries globally, because internet is global and it is neutral. So naturally, it requires a currency which is global and neutral. So that Bitcoin was made for that use case where a server, let's say, resides in USA, a client, let's say, resides in India, and the request is coming from India to US server, and you need a payment for that. So that's what Bitcoin was made to solve, a neutral protocol for native payments on the internet in the form of micropayments. The layers of protocol stack which we were talking about just before. On the right, you see is the traditional protocol stack of the internet, the TCP/IP protocol stack, which has the application layer, the transport layer, the network layer, and the physical layer for our purpose right now. On the left, what you see is what is becoming the Web3 version of the internet with blockchain integrated, which is having the application layer as it is and the physical layer as it is. Application layer is where you build. And below it, you have the transportation of not just data, but of tokens as well. And by tokens, I mean any objects of value. We'll come to it also again. And these are making up the transactions on the BSV blockchain. And transactions are added into blocks. And blocks are transported and communicated and propagated by nodes. Nodes are the BSV blockchain node that makes up the ledgers. They are the server providers who are maintaining the ledger and who are validating transactions and adding transactions to the blockchain, where blockchain is the ledger of all transactions. So that makes up the transport layer. And then you have the network layer, which the upgraded version of the internet protocol is transitioning already to the next version, which is the IPv6 version of the network layer. And that seamlessly combining with the BSV blockchain becomes the new stack of the internet for applications. If you have understood this, then let's go forward and understand about the data structure of blockchain and how that is coming about to solve a very specific problem that's required to transmit anything of value. For that, we first need to understand the need of cryptography and the primitives of cryptography and why that's required. So we have started with paper ciphers way back. And in 90s, there was an evolution and we had the first cryptographic machines that got developed after the World Wars, where the Enigma machine first cracked was used to crack encryption and decryption of cryptographic codes. But that's where cryptography just began. After that, with asymmetric cryptography that was developed, we could do digital signatures. Now, if you can do digital signatures, the checks that you have in banks, which are physical, which you sign physically, this could be a good implementation where digital signatures with your cryptographic key pairs, where your private key is kept with you and your public key is revealed to the other person, who can check whether the signature of any message that you're signing is by you and only by you. So it's authorized, particularly, which can be verified also by a computational device without any manual intervention. So that's what makes it a better system. So the idea of signing digital checks on the internet with cryptographic key pairs could open up the gateway to solve the puzzle of digital cash on the internet. And that's what was used by Bitcoin going forward. But there are more problems to solve than just signing digital checks. digital messages on the internet, because there is a problem called the double spend problem that is not present when you are transmitting email messages or any other message for that matter, peer to peer between computers. But the moment you have anything of value, it becomes a problem of double spending. Let's understand this. So you are sending an email to person A, and then you're sending the same email or a copy of that email to person B. Copying data does not have any effect on the value of the data. That's totally fine, because you can copy data and send another copy of the data, and that's not changing or making any problems get created. But the moment you have something of value, I'm having, let's say, $1 and I'm sending that $1 to you, I can't send the same $1 to somebody else because that's already spent. So if I make another transaction signing even digitally the same dollar to another person, that's called the double spend problem. Now, why is that a problem? Because to be able to find out then which transaction among the first transaction and the second transaction that I did, which were both for the same dollar that I spent, if both of them have occurred and I have signed both of them, then which of them would be valid? Because you would be considering that the fund you received is valid, and your friend would be considering what the version they received is valid. Now, both can't be true at the same time because it's only $1. So, the traditional way, the easiest and the most straightforward way to solve it, if you think about it, is that we put one witness or one central server that witnesses every transaction. If it can witness every transaction, then it becomes the authority and we can rely on it to tell us the sequence of transactions. And if the transaction 2 that I did came later, then that would be rejected and the first transaction would be accepted, right? So that's the easy way to solve the double spend problem. But the problem doesn't end there, because imagine having just one email server for the whole world. For the whole worlds of email, billions of emails per second to go through, only one email server for the whole world, one entity providing that. That is already infeasible for email. Now imagine that for even more valuable objects than email, which is all of your financial assets getting transmitted on the internet. That certainly can't be having such a huge dependency on a single server or one entity for that matter. So we certainly need distribution of and replication of this requirement of a single server or a single witness who can solve the double spend problem. If you're able to follow me through this, then you will understand why the need of blockchain is coming through. So what we require is a distributed or replicated financial ledger with independent witnesses. That's what the requirement is to establish the neutral protocol layer of the Internet of Value, right? So let's try to go about solving this together. There have been many attempts before Bitcoin to get to the answer of a digital cash system on the internet, but all of them failed, and Bitcoin was the first one that succeeded in solving the double spend problem and the general problem of digital cash successfully. DigiCash was first started. Mondex, eGold was very popular, which actually gained a lot of traction, but in the end was taken down by the regulators because it was doing money laundering. Bitcoin, the way it was launched, was actually the final solution to this problem, you can say, that actually achieved a successful peer to peer cash implementation, which was being attempted for more than 2 decades before it. On October 31st, 2008, Satoshi Nakamoto, an alias standing for pseudonymous entity, came into the picture by posting on a public forum that he's working on a true peer to peer digital cash system without any trusted third party. That was the problem statement. And that's what launched Bitcoin a few months later in 2009. Now, the technology behind Bitcoin that actually enabled the solution to the double spend problem was the blockchain. Blockchain was made as the replicated, immutable data ledger with global witnesses for data integrity that ensured data integrity. At the core, the data integrity problem was the most important for Bitcoin to have auditable ledgers which are replicated and which can be trusted. And the most important property of a ledger is its integrity, that it's not tampered with because it's valuable financial information. Well, the scope of blockchain goes beyond just valuable financial information at this layer of the blockchain because anything which is an important document requires integrity. And the blockchain solution, the solution that the technology of blockchain provides, solves for any requirement of data integrity anywhere, not just on ledgers. And we'll come to the applications also of it later on. So that is what you have as the blockchain, the global data integrity layer for every document on the planet, which provides a timestamping service which timestamps and records all data, all events on a single timestamping server that's replicated across the global nodes that support the network and keep replicas of the common ledger. But there is a problem. There is a catch that comes the moment you replicate the ledger, which is that network theory says, and that's what is the problem that comes in, that different transactions come in at a different sequence in different geographies where the nodes are running. So if everybody's having different set of sequence of transactions, then how do you have a common replica of the ledger? So that's the problem that requires another solution that the blockchain solved completely, which we'll be looking into next. We need a mechanism for convergence of the replicated ledgers, or what we call as consensus. Without a consensus, you would have replicas of the ledger which are not in sync with each other. So we need a common consensus system which can bring all of them to a common shared source of truth. So that's the key innovation that blockchain solved. So how does it work? It works by replicating the ledger as we learned first. Not just one entity keeps the ledger, but many entities keep the ledger. It is an immutable ledger, which is a requirement for any good financial database anyway, because immutability has many good properties for just even a normal database to be better than a mutable database. In fact, you would see immutable databases are performant and more scalable than mutable databases or place-oriented databases, which were made in an era when data was scarce and data space was scarce. And later on, with more and more data storage available, it became more reasonable and more succinct and better to program and better to write programs for, better to store data as immutable databases. So, and that's anyway a requirement of financial ledgers as write once, read many times structure. So that's what makes up the core of the database design, the ledger design of the blockchain, which is to have an immutable ledger where records can only be added to it. And an added property that was used by the blockchain is to have hashes used for integrity, which is a core of how blockchain's functionality is achieved. We'll come to it next when we look at the cryptographic primitives, what a hash is exactly. Then the next element to solve this problem in blockchain was the idea of global witnesses. We'll come to it again with the SPV wallets that we have and the block headers that get used. But essentially, we want as many witnesses as possible. This idea is very key to understanding blockchain. We want to make the proofs public, the block headers public, the hashes public, and spread and widespread as fast as possible, as vast and far and wide as possible. Every single IoT device, if it has the chain of headers that makes up the blockchain at the core, it would be a witness to what happened. It knows what happened, even though it knows only the data print, a very small data print to verify, but it still is a witness. And that's what would provide us the maximum distribution and maximum witness capacity and the maximum security, because the more transparent it is, the more witnesses there are, the more secure the chain is. So that's at the key of how blockchain is a distributed data integrity system, which is very ingenious. Next is the consensus problem I was telling you about. The moment you have the replication, you need to solve for consensus between those replicated ledgers. So the technique used in the Bitcoin blockchain when it was launched and what is used by the BSV blockchain is the proof of work technique that we'll be learning next. That's for consensus, achieving consensus between the different replicated ledgers. Then comes the cryptographic signatures of what we looked at before, which was to sign digital checks. So how do you authorize the spend of Bitcoin? That is done by you having key pair held by a wallet, a key pair that holds and controls the signing of every asset that you have. You will be signing it cryptographically. So that's a key for automatic verification and auditability of transactions, which can be verified independently. So one wallet who is receiving should be able to independently verify a transaction that it has received. And that's a key without needing a third party to verify it. So that's how blockchain works, all these elements coming together. Now, to understand it more deeply, when we'll be going it further deeper down into the data structure of the blockchain, what makes up the blockchain, we need to understand three cryptographic primitives for that. The first is hash, and the most important is hash. There are multiple hash functions, but let's understand what a hash function is. So in cryptography, there are functions which allow you to check the authenticity of any data, but by passing it through what is called as a hash function. Any size of data can pass through it in this function as an input, and it would give you a consistent size output of, let's say, 256 bits, because that's what is used in the Bitcoin uh, blockchain's hash function, which is SHA-256 algorithm. This is the function that takes in any size of a file. It can be a movie that I'm downloading from your server to my browser. And your server can tell me about a hash that is verified by me that I received the movie completely without any tampering of the movie. I'll pass it through the hash function to check whether the hash I'm getting is the same as the hash that you said you have. Once we can check that, we know that the movie was not tampered with or changed in the middle by somebody else. And movie is not that important to be changed, but there are more important financial documents and especially digital checks that require tamper evidence and tamper resistance. So you need to check the hash of the transaction that happened, and that's what is providing the integrity. If we can make sure that the hash is correct, then the transaction was not tampered with. So that's what we're trying to achieve with hashes. And the entire blockchain is simply a list of all transactions that have happened throughout the history from 2009 till right now and forever. That's going on. And if you can have one hash to represent everything that happened, that's what is the technique used by the blockchain as a chain of hashes block hashes that get linked. We'll be diving deeper into this and understanding it more deeply. But essentially, you can understand it as the equivalent of physical fingerprints that you have, which can uniquely identify you in the digital world as hashes. The next concept you need to understand is key pairs. So there's cryptographic techniques, multiple one of them. The one used in Bitcoin and the BSV blockchain particularly is the ECDSA or elliptic curve cryptographic technique, which has a public key and a private key generated through a random number, and that is kept secret. The private key is kept secret by you, and the public key is used to validate your signatures by somebody who's receiving them. That's a key element used to make up the transactions, which are the digital checks for our purposes, which have the digital signatures attached. And the validators or the miners or the nodes who are providing the ledger, maintaining the ledger as we talked about, they are going to be performing the verification on these digital signatures that whether the authorization was valid or not, whether you actually consented to giving away your assets or not, whether the transaction was valid or not. So first problem was to solve for the tamper evidence. So you have solved for the transaction that you have received, it's not tampered with. Second, you checked it's not, it's valid, it's a valid signature. So certainly it's not tampered with and it's a valid signature. So we are good to go ahead. So those are the important things you need to understand. And interestingly, in these three primitives that I told you about, there's no encryption. So the blockchain, which is unpopular opinion, which is not known, is that it's not having any encryption. It's a transparent ledger having the hashes and the signatures used without any encryption anywhere in the protocol layer of the blockchain. Now let's get to the next phase of understanding why we need proof of work and how proof of work actually solves and achieves the problem. So, to solve the double spend problem that we looked at, we need a global timestamping server. And this server needs to be a distributed system, right? So, that's what we're trying to achieve, a timestamping server that can timestamp transactions so that we know what came first and what came next, because that's the important problem we're trying to solve here. The global sequence of transactions that have consensus across the whole world between many different servers, nodes that we call them. You will also get to know them as miners. The diagram on your screen shows you the structure of the blockchain at the most basic level as the linked list of hashes. So the first block that you see is having a list of transactions that happened in the first block during that time. So the blockchain you can understand as every 10 minutes you're having a new block. And what is added in that block is the list of all transactions that have happened in that duration while that block was getting created. And then once that block is created, the next block is started to be worked upon, which adds the list of all transactions that happened during its own time interval. And like that, if you go on through the first block ever created on the blockchain, which was in 2009, that had one transaction only, because only one transaction happened at that time. And sequentially, you had a chain of blocks added. Every 10 minutes, a new block added, approximately 10 minutes, a new block added. And that just goes on until now we have that chain running without stopping. So it's a very robust network system which is incentivized and which has many players who are competing to create these blocks. These players are the miners or the node providers who are maintaining the ledgers, who are creating blocks, and who are adding and verifying all transactions that they have witnessed on the network. And they are getting consensus between themselves, between other node providers. So that is the structure of how the blockchain is working. Now, these blocks are referencing the previous block before them. As you can see, as the arrow from the first block on the right to the block behind it, that's referencing the previous block. Now, what is it referencing exactly? That's what we'll see next. So essentially, it's a linked list of blocks. For that, on why we even created blocks, why couldn't we just add transactions as a list of transactions and be done with it on the ledger? Like normal databases, they have transactions and that's it. You don't have blocks. Why need blocks? What's the problem? So the problem is the problem of convergence, as we discussed, of consensus. The moment you have replicated ledgers, you're having a problem of ledgers which are not having the same sequence of transactions, which are not synced. So there is a problem of convergence onto a single shared source of truth. So how do we come to it? The way we are solving for it, but the way the blockchain solves for it, is to create blocks where blocks is what you accept and reject between different miners. So at once you can have multiple transactions or sequence of transactions accepted or rejected by a miner or a node maintainer. So you get consensus in blocks instead of at a per transaction level. That's important for scalability and important for convergence to be successful. We'll come to it how and why it's important even more. So let's say we have created the structure of a block. Block has a list of transactions. Now, if you accept the block, you accepted that entire list of transactions as the sequence, and then you're working on the next sequence of transactions that's adding to the list of transactions on the correct sequence. So sequence anyway has to be a list, so it makes sense to be a block, right? Now, the problem that immediately comes is if there are thousands of participants on the network, there can be thousands of block proposals within 10 minutes and thousands of different versions of the sequence of transactions, right? So if there are thousands of people competing to have consensus of their block proposal to be accepted by everyone, we would get nowhere. So there is a requirement to make it more difficult. What if we made the proposal more difficult to create? And we can just check that a proposal is valid or not and decrease the number of proposals that's getting created, because anybody, if they can create a proposal, then it would just get spammed and we won't have consensus. So the problem then is if instead of 1000 blocks we had just, let's say, one block proposal created every minute, let's say, that could solve the problem potentially. But around 1.5 minutes there would be another proposal and they would then be competing, right? And then you would have a few proposals running within a few minutes, which is not enough of a gap for the global internet to get consensus on very quickly. So that's a very good value of 10 minutes. That's the standard set by the BSV blockchain to get consensus. Give enough time to have the difficulty set at a level that the block proposals are decreasing to a rate of only one proposal every 10 minutes, approximately. That's the targeted level. Once we reach that, we are able to get a control over the number of proposals that's coming in, and only the difficult proposals that took 10 minutes to be created, that are going to compete, and that's enough time to get consensus on the global network, right? So that's why we have a proof of work technique getting used. We'll come to how the difficulty gets increased of a proposal, of creating a proposal, the cost of creating a proposal, of a block proposal. So the idea of proof of work originates from the Adam Back's hash cache system, which is referenced in the Bitcoin white paper also. Now, this system was made to reduce email spam, as an example. Let's say you're getting hundreds, thousands of emails. That's a common problem. And the cost or the number of emails sent by the spammer is in millions. And the cost also would multiply at that level. If you put even a small cost to each transaction, the cost of the entire set of spam emails to be sent would be huge. So that would reduce the spam and denial of service attack also. So that's a good technique that was adopted by the BSV blockchain to be used as the block proposal difficulty method. Now, what is that? It's very simple. It's again using the hash function. We are passing the message to this function, and the output you get is of 256 bits, right, to this function. The first few bits of this hash of the email in this case, or the block in that case, in the blockchain's case, if you put a criteria that the consecutively you need to get, let's say, 14 zeros in the hash, that's a difficult criteria to meet. So this is a technique that's used, that you have to iterate through a lot of random values to find out a value that, when attached to the email, gives the hash value with 14 consecutive zeros, right? So that's essentially the core of the technique. And we'll dive into this deeper of exactly what happens in the block header of the BSV blockchain. So four strings are concatenated or attached to each other to calculate the hash of the entire block, which needs to be having the requirement fulfilled of the difficulty that you see below the screen at the bottom. Now, what are those four elements? They're very simple. The first element is the hash of the previous block. That's what's creating the linked list of the blocks, because every hash of a block has a connection to the previous block hash. It's using its hash in its calculation of its own hash. So it's creating a linked list of hashes. That's what is making up the blockchain at its core, for creating the integrity chain of blocks. So the previous block hash is used first, and then you have the list of all transactions in the current block, right? So we need to have one common hash to denote the sequence of all transactions in the current block that we are proposing, right? To represent the data of this block. So that's what is called as the Merkle root. We'll come to what that is, but essentially it's representing the hash of the sequence of all transactions in this block. That's the transactions hash, or the Merkle root hash that you see here. So once you have the previous block hash, the current Merkle root hash of all transactions in this block, then you add in the timestamp, which is the timestamp value of the proposal of this block, and the nonce value, which is the key value which we are trying to find by brute forcing through a lot of values randomly with brute force to figure out a value which will satisfy the difficulty constraint of the block proposal. So this is the created block proposal that was artificially created to reduce the spam of block proposals between miners who are proposing blocks to each other to a level of one proposal per 10 minutes, right? So this difficulty is set, but how much? Is it 14 zeros? It is 2 zeros? It is 4 zeros? Well, it's a moving average, because the difficulty can increase if you have more computational power that joins in the network. If there are more GPUs, or GPUs become more powerful, let's say in the future, then it would be much easier to find the hashes, find the block hashes very quickly, because those computers will be able to go through trillions of nonce values and find, let's say, 5 zeros, hash with 5 zeros very quickly. So the difficulty would then need to be adjusted to 20 zeros at that point. So that's why it requires an adjusting difficulty based on the moving average of the previous 2 weeks worth of blocks and how much time gaps they involved. So there is an equation there that is a moving average of the previous 2016 blocks time interval that are used to calculate the number of zeros required in the next block proposal based on the previous 2016 blocks that have occurred, right? That creates a dynamic system of difficulty which makes sure that we are always targeting a difficulty level that targets 10 minutes as the average for all the blocks to maintain a consensus and maintain a rate of block proposals to 1 per 10 minutes. If you have understood, say yes in the chat box and we should be able to go ahead. So this proof of work mechanism is able to control the block proposal frequency that we are getting on the internet. And it follows just one rule to achieve consensus. What is that rule? So the longest chain is the authority chain, is what is followed because it has the maximum support of the network CPU power or the nodes or computation power that they're carrying. That's supporting the longest chain because that's having the most proof of work done. So most of the honest nodes who are having the correct sequence of transactions, they would be naturally having the longest chain. So it's a very tight knit competition happening between the nodes to create a block proposal, or if they have not created, then accept a block proposal very quickly because otherwise they risk getting orphaned. That is the block proposal they were working on. If they insist on keeping to work on that block proposal without accepting somebody else's proposal that they have already found a block proposal, then it's a game theoretic system. Other nodes might accept it and start to build on top of it, of that proposal, and their proposal will be left behind because now they have taken a heavier risk of betting on themselves. So that risk is there of either accepting or keep working on their own block proposal. That game theoretic competition, as we'll get to know, is a Stackelberg game that gets created that's bringing the chain to convergence naturally because risk of getting your block proposal orphaned makes you follow the larger consensus and start to build and try to compete in the next block, right? So that makes the chain extended faster. And the moment another block comes after the first block, the tie is broken, and then you have the blockchain continued with the longest chain winning out as the authority chain. The good diagram to explain this, a very good diagram, would be 1 second. I think is this diagram. Yes. So here you see multiple chain tips competing. What you see on the left is the existing block that's accepted, and many competing miners are building on top of it. Then you have one block proposal on the top that has competed but not able to win. So it's orphaned. The dark blue ones are the orphaned ones. And the longest chain is the one which is in teal color or the light blue color. That's making up the longest chain. So the orphaned one was trying to compete and have another block proposal. Then soon you had a tiebreaker because both of these blocks were created approximately the same time. These block proposals by different entities and different sequence of transactions. So because they were created at the same time or approximately the same time for the network, some of the miners would have accepted the first block because they were closer to that node. Other set of miners would have accepted the other block because they were closer to that part of the network, and one of these two would win. Now, how does that happen? The next block after that is the tiebreaker, because it's very rare to get two blocks consecutively coming at the same time, right? So the chances of that happening is very less. So the moment you have the tiebreaker block coming in next, that would make sure it becomes the longest chain, and then it just continues and you have the longest chain continuing, right? So the probability of having continuously same block proposals achieved at the same time across the network is lesser and lesser to have it done consecutively. So the blockchain naturally ensures convergence to a single chain as the longest chain, right? So since you have understood that, let's try to understand the data structure more deeply of the blockchain. So as we learned, the part of calculating the block hash was four elements, right? The previous block hash, the current Merkle root hash, which is the list of all transactions hashed in the current block, the timestamp, and the nonce value, right? And then this is what makes up the block header. These four values is what makes up what we call as the block header. Every data packet we sent, any item of envelope we sent on the internet as a data packet also has a header, right? These protocols always have a header, and even with the block proposal packet, it has a header, a block header, and then a list of all transactions that it is proposing as a sequence of transactions. So this header has these four values. Now what we need to understand is the list of all transactions and how we get the Merkle root hash, because the Merkle root hash is able to represent all transactions in a sequence that have happened with just one hash value in the current block. So for that, the structure that is used is a Merkle tree, which is a binary tree of hashes. It's very simple. It's if you arrange all of the transactions in a sequence, you hash each one of them and get a hash. That's the leaf that you see here, leaf nodes, which is the data 0, data 1, data 2, data 3 at the bottom. Each one of them is hashed to get H0, H1, H2, and H3. H0 and H1 are hashed together in the binary tree fashion. So you get H4, H2 and H3 are hashed, you get H5, H4 and H5 are hashed, you get the root hash, right? So that's the Merkle root hash. And that's what is uniquely able to identify and represent and validate the sequence of all transactions in the current block. So this is what makes up the data structure of the blockchain. Now let's understand another element that's required for the blockchain to function, which is the incentives. Why should the node providers or the miners do the proof of work, which is a costly puzzle to solve, and also validate transactions for the network? They do it for incentives, and that incentive is created in the blockchain mechanism with two elements to it. The payment happens in bitcoins as the tokens to pay for the transaction fees, and new coins of bitcoins that come into circulation each block, which is a consistent amount that comes in each block, is also received by the miner or the proposal which won. That is what gets these two incentives, which is the block reward coming from the new coins coming to circulation, though it's decreasing in value every 4 years in a geometric progression starting from 50 per block. Right now it's about 3.25 per block, and it keeps on decreasing every 4 years, halving every 4 years. So that's the block reward, because new coins that are coming into circulation are subsidizing the incentives for the miners to support the network. And transaction fees collected from all the transactions that were added in that block proposal, right? That's the incentive mechanism used to incentivize the block producers to do the work of verification and propagation of all the blocks and support the network. So that's what is the deep connection between Bitcoin and blockchain. So now you have understood the technology behind Bitcoin, which is the blockchain and its data structure. Now let's understand the economic model more deeply and why it's creating the proof of work successfully. So the distributed node networks of nodes that we had, they required a consensus. And they required a consensus in such a way that the divergence is reduced. And divergence was reduced by increasing the cost of creating a divergence, which is another proposal, right? So that created the convergence onto a single proposal every 10 minutes. And a convergence beyond that is for the risk of orphaning of a block that converged onto a single longest chain. That's what the economic model that secures the blockchain and makes the longest chain win. And all of the computational puzzle that's burying all the transactions behind blocks or inside blocks and burying them block by block. If your transaction is 10 blocks behind, that means it's even more secure because it's higher risk and higher, even lesser likelihood for all the 10 blocks to be changed, because the history cannot be changed now. Essentially, what we have created is a very tight knit, tamper resistant, reliable ledger of data that can be trusted because none of it can be changed. So that's what we have here. And the network effects in this model make sure that all the miners are aligned in their incentives to support the network as honest nodes. This game theoretic system, if you want to dive deeper, you can study this as a multi-leader, multi-follower Stackelberg game, where each block producer who's in this market competing to be a block producer is being a leader when he proposes a block, or if he follows a block by some other block producer, then he becomes a follower, while that person or that entity is the leader for that block. So it's a multi-leader, multi-follower Stackelberg game structure of incentives that makes sure there is a profit maximizing behavior that leads to network convergence despite the absence of a central authority that can make the list of all transactions as a common consensus of what is true, what is false. And it also incentivizes miners to invest into not just hash power to increase the solutions, the speed of them getting a solution to the block puzzle, but also to increase their block propagation speeds. So that's the core of the theory of blockchain and proof of work. Now let's get to the use cases and what we can build using this blockchain. The first thing to understand is the vision of the value layer of the internet. That's known as Web3 also. Many circles you'll get to know as MetaNet or Finternet, all names for the same thing, which is the value layer of the internet. In the protocol layer of stacks that we saw, it's becoming the layer of transmitting any object of value, which is generally known as any token. For that, you need to understand the idea of tokenization also. So, first and foremost, if I tell you that our aim is to bring the whole global economy on chain from off chain, very much like the internet brought data from offline to online. Similarly, now we're trying to achieve the entire global economy to be shifting from off chain to on chain, right? So that's the vision that we're trying to achieve. And there's many applications that's needed to achieve that vision. The most important object that's required here is tokens, because it's a ledger. The blockchain is a ledger. And in order to use the ledger, you first need to represent objects on the ledger. Only then you can track them or transfer their ownership and get benefit from the blockchain. So the first process is tokenization, which is the process of representing objects of value on the ledger as tokens, right? So that's the process of tokenization. They can be digital objects, they can be physical objects, and they once they're represented on the blockchain as tokens, then you can transfer them and you can write programmable contracts onto them. You can automate them, you can validate them, you can verify their ownership. All of that can happen once you tokenize any object on the blockchain. That's a very important concept to know of. Now, this token is very different from the native token of the blockchain, which is Bitcoin in our case. or there are many different blockchains out there. They have their native tokens, and those tokens are used to pay for the transaction fees. As we learned before, they are not the tokenization output that we get from creating your own token, but they are required as a native token to finance the mining operations and for the network to be supported. So that's the transaction fee token that's used. That's called a cryptocurrency token. That's different from or the native token. That's different from the tokens that you create on your own for your applications. Now, what are the tokens that you can create? We'll learn next also. But for that, you need to also understand the concept of Web 2 and how we are moving from Web 2 to Web 3. So, the version of the internet in which you have monopolies forming, which is the current version of the internet, where there are huge network effects that are part of making any marketplace function, because the more suppliers you have, the more buyers you have, the more network effects you have. But all of that is accumulated by a monopoly agent. In the case of social network, that's Facebook. In the case of search results of links, distribution of links, it's Google. Distribution networks, they're all distribution networks essentially. Distribution of content or posts by Facebook, distribution of links by Google, distribution of videos by YouTube. All of them are distribution networks, and they monetize distribution, right? Because everyone has to connect to them to get distribution. You pay them to get more distribution, which is advertisement. You do not pay them and post something you don't like or they don't like, you get less distribution. That's censorship also. So both of these things are tapped into and connected to the idea that there is a monopoly distribution network, which is benefiting from all the network effects. Now, the idea of Web3 is coming in where the cost of distribution, which was taken up by all these monopoly players to gather in all the network effects, is distributed itself and reduced in cost, because now you have a competition between not just one player maintaining the entire private database for distributing and connecting everyone. It's many players who can openly compete. Every 10 minutes they have to compete, so it's a very tight competition where there cannot be any one monopoly forming, and all of them competing to distribute transactions, right? So that's what makes up a system which is higher quality and lower cost and more customization, because that's what happens when you have a market created instead of a monopoly. Now, what type of tokens can you create if you can create your own tokens? For that, you need to just understand two token concepts. If there is any good or service that you want to represent ownership of, that will be a utility token, which you can have it as a reward point, a ticket, a coupon, any good or service represented in ownership. Let's say um, you're buying an iPhone, it has a barcode, there can be a digital product passport for that iPhone, and then there can be a digital twin for supply chain objects that are for B2B goods that are transmitted. So any good or service in the economy, there can be a utility token created, which we call as a simple token, a utility token, which can be created by any business. That's why it's simple. Next comes the concept of a security token, which is to tokenize more of the financial layer of the economy, which is made up of shares, bonds, mutual funds, and many other financial instruments, currencies that makes up the economy. And they require more regulation. Not just any business can just issue it on their own and distribute to their customers. It has higher regulation. That's why it's called a security token. And there's a different requirement that's met with a different smart contract, different programming for it that satisfies those constraints, right? We are going to be making those tokens as we go forward. Let's look at some of the use cases for these types of tokens and what you can do with them. With shares and bonds and other financial instruments, the first immediate benefit that comes in is that you have instant settlements. Because right now, if you try to settle a share, they are held by depository institutions who have a huge settlement time of multiple days. If you sell a share, let's say, you'll need at least 2 days for it to settle to your demat or dematerialized account. And that's what can be made in an instant. You can reduce that cost to instant transactions globally, and that can be for cross-border payments also, instant settlements. That's another good use case of a tokenized currency, which is also known as CBDC or stable coins. If it is issued by this authorized central bank, then it's called a CBDC. Otherwise, it's called a stable coin. If it's issued by a private player, another use case can be in the digital world. You can represent digital rights to content as read access to a file or write access to a file. They can be tokens themselves. And you can actually count them. Let's say Photoshop or Adobe marketplaces are there, which are for stock photography or stock assets or digital assets. They sell view access of, let's say, 200 views for a file. Now, how do you count these views? The way you can count them in a way that's very reliable is that every view would require a token. And if they're buying 200 views for a file, then they're buying 200 tokens, unique tokens to get access to that file. So that's how we can gate content with tokens and digital right tokens as well. That's the idea that created NFTs, but NFTs were popularized in a form that was not in sync with this particular original use case, rather became a speculative market. But that's a topic for another day. Then you can actually represent real objects or supply chain objects, as we were discussing on the blockchain, and track them between businesses, because supply chain happens between businesses to businesses before it reaches the end customer. So the important token that's important there is the digital twin for that object in the supply chain. Like that, there are many use cases. Any one of you can think of them, of what would be required in which sector of the economy where blockchain can actually provide a value by having the data integrity layer or the financial value layer of the internet, where you need to track objects across different entities and you have automatic transactions and validations and verifications happening. Now let me show you the blockchain, how it looks like. So what you see on your screen soon, I think you should be able to see the What's on Chain Explorer. So very much like you have the Internet Explorer when Internet was launched. The same way you have the Blockchain Explorer to explore transactions on the blockchain. So when you create your own transactions, you would be seeing that here on the BSV Blockchain Explorer also. Now, what you see on your screen on the left, on the right, extreme right is the latest block, where hopefully you see my mouse as well. Gorilla Pool has mined the latest block, 15 MB megabytes in size. That's block number 888,455. That's the latest block of the blockchain that has been going on since 2009 till right now. And this is the latest block having the list of transactions that have happened in this block. The block before that is created by another node or another miner called CUVVE. That's its brand. Before that, there's Tal creating another block. Before that, you see SA100. Before that, you see QD Link. So all of these are different network participants. It's not one monopoly entity. It's multiple players competing to create blocks on the network, right? And you can click on it and go inside any block. But first, I want to show you more details of the block. So the first number that you saw, which was the block height, right? 888,000. That's called the block height of the block. New blocks are added to the blocks. That's why you can understand it as height. The more the block is buried below, the more secure it is. That's why it's a height. You're burying transactions into blocks, burying blocks by more blocks, and it's getting more and more secure as it goes down. Then you have a time interval for the block, which is this block took 1 minute only. Then you have 9 minutes taken by a block, then 1 minute taken by a block. Like that, there are different time intervals for the block. They're all trying to target a difficulty of average of 10 minutes, but it's not fixed that the interval is 10 minutes. Now there are different number of transactions in each block. The 95 in the first block that you see, 317 in the other block, 16 in the next block, like that. So depending on the demand that happened in those minutes where that block was getting created, all the transactions at that time interval will be included. So it is also dynamic. Depending on the demand, the supply of that block size is also created depending on the number of transactions that's required. So let's go into, let's say, this block and look at what we have here. So 888,454. This has two confirmations because two blocks were created on top of it, and you have multiple transactions inside it. So that's how you view into a block, and you see a list of all transactions that have happened into it. What you also see is the Merkle root. You see here, this is the Merkle root that we looked at. This is the binary tree root hash of all transactions listed below. And it has 317 transactions. There is a difficulty that it's targeting right now, number of zeros that's required, and it has a total fee collected from all the transactions that have happened. Now, if we look at any transaction here, let's say we look at this transaction. Now, each of these transactions you would see also has a tag here. This tag is from an application that generated this transaction. Just like your packets, data packets, if they are sent on the internet between servers, the applications are actually creating those data packets or database entries. Like that, the same way, there are different applications used by different participants or wallets or users who are using the blockchain to create their own transactions while interacting with an application. And you as a developer are going to create such an application and have such a tag on the blockchain for your own transactions or your own applications transactions. That way you can even market your application and have that used more. That's what we have here. Let's go inside a transaction. So inside a transaction, you have inputs and outputs. We'll come to it in the next section when we understand the data structure of a transaction. What we understood till now was the data structure of the block in the blockchain and how we explore a transaction, how we explore a block on the blockchain explorer, which is the Watson chain explorer that you see here, right? So this is just what a transaction is. It has a transaction ID. If you search here, you would also, if you just paste a transaction ID here from your application, when you generate a transaction, you would need to search here, paste a transaction ID, you would open the transaction here, you would see the fee rate or how much fees you paid. Here it was 1 Satoshi. What is 1 Satoshi? It writes 1 e raised to minus 8, right? So 1 Satoshi is the smallest unit of a BSV, which is Bitcoin. The smallest unit of it is Satoshi, standing for 10 raised to minus 8 Bitcoins. So that's only 1 Satoshi for transaction fees in this transaction. And you have a size of 540 bytes for this transaction. So you can see a very small transaction of only one input and two outputs. We'll understand what these inputs and outputs are also very, very soon. Okay, coming back to our presentation, this link is there for you to explore on your own as well. watsonchain.com, and a wiki for understanding any concept on your own is also shared on this slide. It is at docs.bsvblockchain.org. You can understand the entire structure of the documentation of the BSV blockchain if you go through this to begin as an application developer to understand the BSV blockchain from start. Okay, coming back to our presentation and continuing with understanding transactions now. So transactions, as you saw on the blockchain with the first transaction, have multiple inputs and multiple outputs. Now, what makes up an input and an output is the Satoshi amount. You are holding Satoshis in these transaction outputs, and these are unspent until they get spent by a future transaction. The easy way to understand this is by looking at a transaction, and let me explain you there. Let's go back to our blockchain explorer and understand what a transaction looks like. I hope you can see what's on chain screen, in which you would see a transaction, and it has one input and two outputs. Now, you see a total value here of Bitcoins 1.499. This is the total input value unlocked. And the input value here was given by only one input, so it has the same amount, which is the 1.499999353,184 Bitcoins. Output value is also there. If you can see, it has 1 point same value, just reduced by 1. The difference is only 1 Satoshi in both of them, because that was what was paid to the miner for fees. Now, what is this? Essentially, when you have a cash system, your physical wallet is the wallet provider, right? It holds all the notes and coins. In that case, it is the inputs. It's holding all the inputs that you can create in a transaction and spend it. So let's say you want to make a payment of 150 euros. Okay. How would you pay 150 euros if you have 200 euro notes in your pocket, in your digital wallet, in your physical wallet? So you would simply take 200 euro notes, you would give it to the other person as cash. So in this case, it would be two inputs. Two inputs which will be unlocked. Both of them would have their values of 100 euro token in the first input, 100 euro token in the second input. Both of them would be spent, unlocked, right? And they would create outputs. Now, if you need to pay 137.55 euros, you can create one output of 137.55 euros, and the other output would be the change output. You can give yourself the difference, the remaining difference, back to your own address, your own public key. You can send it there, and that would create the two outputs of different values in size. The only difference here, what you can understand, is in this cash system, the denominations are not fixed. In a normal cash system, like in euros, let's say, you would have only a 10 euro. You can't have 3.5378 euros as one coin or token. But in this case, you can, because it's a digital system and it's a digital cash system. We don't have that restriction of have fixed denominations. So the denominations are variable here. So, and you can have any number of notes and coins unlocked essentially as inputs in a single transaction. You unlock all of them by giving the correct signature to all of them. So you are able to prove that you are the owner of them. You're able to unlock them, spend them as inputs. Then you have a total number of input value created. You can even have different entities or different owners of different tokens come in. Let's say you can pitch in as a entire batch together, everyone pitching in 1 euros as one input in a transaction, and collecting, let's say, 200 euros together as all inputs of a single transaction. And you can spend them as outputs to only one entity as a payment, let's say, or to thousands of people as a donation spread out to multiple people. It's up to you how many inputs and outputs you create. The only rule is that the total value of output has to be less than the total value of input. And the difference is the transaction fees. Why it has to be less? Because you can't create tokens out of thin air or create value out of thin air. In this case, you can't create new Bitcoins, right? So that's why it can only be less. The number of tokens you give has to be less than a token number of tokens you unlock, right? So it has to be less than a total number of input, and that's all. The difference is the transaction fees. That's the important bit you had to understand here. Is all that understood? Then let's move on to the next section. What you see in this output is a address and a value that it's holding. Now, this is an output which is already spent, because if you see here in this transaction, it's already marked that it's spent in the next transaction as input number 0. If you go here, you would see this is the new transaction where it was spent, and this was spent again in a next transaction here. So that, like that, the chain goes on. The moment you come across an output which is not spent, that's what is holding the current bitcoin, and the bitcoins have not been unlocked and spent and flowed to another output. So it's called a UTXO, or a unspent transaction output. Let's come back to the presentation and understand UTXOs more deeply. So UTXO, which is the unspent transaction outputs. So current bitcoins in circulation, all of them in circulation, which are right now held by different people, all of them are held in unspent transaction outputs. Think about it. The moment they are spent, they're not being held in that output. It's already spent. So it's held in another output that's holding it as a UTXO, right? So all the current distribution bitcoins are held in a UTXO. Your wallet is also simply a UTXO manager, just like your physical wallet is a notes and coins manager. Same way, your digital wallet of your Bitcoin wallet is the manager of UTXOs. It just maintains a list of outputs that it controls, that it can spend in any transaction that it wants, whenever it wants, because it has the key pair to unlock them and spend them, authorize the transaction and unlock them, right? So that's what is the structure and the concept of UTXOs as cash. Now, this diagram shows you the entire picture in one image. On the top, you have the block headers, which we understood were making up the chain of linked blocks, right? Now, they had a Merkle root, right? That's what you see as the tip below the R, which is the Merkle root hash. And then that is going into a binary tree. Finally, you have transactions, which are the leaf of that binary tree of hashes. And then you have the transactions, which have inputs and outputs. The outputs, these are essentially the cash system that's happening. The outputs get spent as inputs in a subsequent transaction. Whenever they get spent, it need not be a subsequent transaction, just the next transaction, because here you see a transaction 3 is happening way ahead of transaction 1, and the output there was spent after many days as input in the next transaction. Just like your physical wallet, you need not spend it as the next transaction immediately. You might hold it for many days or months and then spend it later in a future transaction. And the other input can come in from a recent transaction. It doesn't matter, right? So this is what is showing you the entire structure of the blockchain with transactions, with inputs and outputs in one image, right? So if you have understood this, you have understood the data structure completely of the blockchain, why we have the proof of work mechanism to restrict and converge onto a single chain, how you have transactions, and that completes the theory of blockchain and pertaining to Bitcoin in particular. Now we can do more than just financial payments with transferring Bitcoins, because you can create your own tokens as we discussed, right? So you can create your own tokens and you can create your own programmability of those tokens. Now, how do you do that? For that, you need to understand that Bitcoins are locked in a custom function, which is called a predicate, which is holding the coins or the tokens as we see. Let's go to the Explorer again to understand this concept. You see the transaction we were looking at. I hope you can see my screen again. Yes. So this is the Blockchain Explorer again. We are back to the same transaction. It has inputs and outputs. Now let's go to this section, which is the scripts. Right. The scripts actually show you the byte level view of what's happening in those inputs and outputs, right? So this was an output number 0, which had 0 satoshis, and this was the output number 1, which had control over a few satoshis. So let's look at this output number 1, right? So it's creating a function. What is that function? It's determining what is going to be the input that's going to unlock the function. What is the criteria for that function to be unlocked? If it gives any non-zero value as its output at the end of its processing, any non-zero value, then it's going to be unlocked. And that's what is a property of a predicate particularly. Why is that? So definition of predicate is very simple. A predicate function is any function that takes any data size of input, but it exits with only true or false, only two as the two possibilities, because that's the requirement of a token, right? Either you can unlock it or it will be locked. There's no partial unlock here. It's either locked or unlocked. It's binary, right? So that's what is a property of any lock. Now, what you have here is an information lock. The information lock is creating your own custom predicate or a own custom function that's could be any function. It could be any requirement in your input data that you are checking against. Let's say the standard payment, it checks against a signature. It checks whether the signature is valid or not. It's true or false. That's why it's a predicate function as a standard payment that checks for a digital signature through the ECDSA key pairs. What you see here, already you see on your screen, the check sig operation code that checks for the signature. But you can write your own custom functions here. That's what is called as a smart contract. You can write custom functions or custom predicates. It could be that I put a bounty out for finding the square root of 25, and anybody who provides the answer, it's quite easy, I know, but anybody who provides the answer would get 1 Bitcoin. I can write that in this function that just multiply the answer you get by itself, duplicate it and multiply by itself, and equal verify, just check whether it's equal to 5, and that's it. I have a very simple script written for a bounty that's given for anybody who solves this, gives the correct answer, unlocks that coin on its own. They don't need to even uh, provide any signature for it or any other requirement. So like that, you can write custom functions, and there's a lot of rich assembly set that's able to provide you ability to script any Turing complete program, because it's a Turing complete script and a virtual machine to process it. Just like you have the Java virtual machine that compiles Java language into the Java bytecode. Similarly, you have the Bitcoin virtual machine in this case that compiles uh, any language, particularly the TypeScript language, which we already have a compiler for, that compiles into this script, which is the Bitcoin assembly code or operation codes, also known as the script language, the Bitcoin script. So just like you don't program in assembly language, but you do program in TypeScript or other languages that compile to assembly finally, Bitcoin has its own assembly that you're seeing right now, and that's making up its own functions or predicate functions, which are smart contracts, which you can program as we go down the lane in the future workshops we might be learning soon. So that brings us to an end of the theory section of transactions. And now let's understand the different tokenization technologies in the BSV blockchain space. There's many, but the most popular ones are BSV 20 to tokenize, because when we are creating a token, what is happening here? Essentially, the outputs that you were seeing, right? That's all the transaction structure is. There's nothing outside of it. Anything you want to do with the blockchain as an application developer is to either create wallets that hold the key pair and create the transactions and maintain the UTXOs. And when you create a transaction, the only thing you can do is inputs and outputs. There's nothing else you actually do. So what we're trying to do is represent a particular type of output of holding some satoshis in such a way that it's not just holding a satoshi, but it's holding something of value also separate from satoshis. The best way to understand it is, let's say we have a metal coin. Bitcoin in this case is that metal coin. Now, if you want, as a national ruler or a monarch, I want to print my own currency. I need to do coinage. I need to mint my coin. I need to issue my signature on that coin, showing that it's the authorized token of my nation. It's my currency. It's my euros that I'm issuing on top of a metal coin, right? But I need the coin to issue it on. The same way, you need satoshis to represent the tokens on, to transmit the tokens and use them, because that's the commodity in this case of the data ledger, which is the Bitcoin as the commodity. Now you're using, just like you use the paper notes right now, paper is also commodity. You're using the paper to issue a token on top of it. The same way you use Bitcoins as the commodity to issue a token on top of it. And that token can represent anything of value. And that's what there are different uh, protocols for doing the tokenization of how you represent the token. Just like you have different programming languages and frameworks, many frameworks, front-end frameworks that have different merits and demerits, same way you have different tokenization frameworks also. So BSV 20 is one framework such like that, and Stars is another framework like that. There are other blockchains also out there, like Ethereum is a blockchain. Many other blockchains are out there. ERC20 is a token protocol that is popular on the Ethereum blockchain, and Ordinals is another protocol that's very popular in the BSV blockchain. Those are the different tokenization frameworks and protocols that you would be aware of when you build an application that requires tokenization. Now we understand wallets. So what you understood was tokens, and tokens are held in wallets, right? And your wallet is what creates transactions. The most important aspect of this, and when we started the entire lecture, was you understood the problem is that we need to have peer-to-peer transactions between wallets, right? For that, we require transactions to be independently verified by the receiving wallet without needing a trusted third party, right? For that, there is a technique mentioned in the Bitcoin white paper when it was launched itself, but never implemented, that the BSV blockchain has implemented completely, which is the simplified payment verification technique, SPV in short. And SPV wallets are a standard in the BSV blockchain space. All the wallets follow that. And when you, as a developer, also make an application, you would also be creating the SPV wallets. And we will be showing you how to create wallets for your users, SPV wallets in particular, and creates transactions using those wallets and view them on What's on Chain in the subsequent workshop that's going to happen tomorrow. Right now, what has traditionally happened in the blockchain networks while Bitcoin was launched, and many years in Bitcoin also, which BSV solved with simplified payment verifications, is that transactions were not sent peer to peer. Even though the concept and the idea of the mission statement was to achieve that, it was never achieved, and still not achieved by most blockchains which do not have SPV. Now, what happens is the transactions are not broadcasted peer to peer, just like you send cash peer to peer. They are instead broadcasted to the miner first, and the miner receives it, and everybody has to connect to the miner to view their or figure out which transaction is their own, right? So they have to scan the entire, their wallet has to scan the entire blockchain to know which transaction is their own transaction. Now, why is that a problem? Is because that's not scalable, first. Second, it's creating a dependency on a third party, which was not the idea in the first place. And it's like having one email server for the whole world's email again, and you are contacting that server. Imagine going through the list of all emails that everybody has received in a whole in one common pile and figuring out your own emails from it. So that's what the system is without SPV. And with SPV, what we have is the transaction goes from your wallet to my wallet directly. And because I have received a proof of the transaction along with your transaction peer to peer to me, which is the Merkle path, we'll come to it, of the transaction, proving that your transaction inputs were there on the blockchain, are part of a valid chain of transactions. And I have received from a valid chain of transactions the transactions that I have received, and I can independently verify the signature and validate the transaction. So I can accept the transaction and provide you the good without having to depend on any trusted third party for validation. So that's what completes the mission statement of blockchain. That's the completion of the peer-to-peer cash system as the SPV wallet structure, right? To achieve true peer-to-peer wallet transaction. Now, what is that structure is explained in this diagram particularly. It's very simple if you understand it. Otherwise, you need not go very nitty-gritty into the details. When you're developing applications, all you need to do is understand you're creating an SPV wallet, which is the right way of creating wallets, and then creating transactions using those wallets, right? But to understand this, the only thing you need to understand is the Merkle root was having the list of all transactions inside it, right? Now, if you want to reference a transaction and prove that the transaction is in the blockchain and it's not something that's spoofed and not part of the blockchain, then you would try to create a transaction which is not part of uh, the blockchain, but the other person will try to do a SPV validation to it. So the inputs that the transaction has received, they would try to validate whether those inputs were part of transactions that were part of the actual blockchain. And for that, they would require the Merkle branch of the transaction getting added to the blockchain. So what you would send them is not just the transaction as a wallet. You would send them the entire Merkle branch. Now, what is the Merkle branch? It is the hash 3 here, hash 2 3, which is a combination of hash 2 and 3, hash 1, which combined with hash 2 and 3 gives you the Merkle root. Now, if you have all of these hashes given to you, hash 1, 2, 3, 2, and 3 given to you along with the transaction, then you can independently verify that the transaction was part of the Merkle root and Merkle root was instead part of the block hash, and you as a wallet have the entire headers from the beginning of the blockchain, from the first block header till the latest block header, which is maintained by the wallet by itself because it's very small in size. It's only 40 bytes in size. So you can maintain the block header chain, which is very small. And even after an entire year, you would only have a few megabytes of increase in the block headers. So the SPV wallet maintains the block header chain. So it has the entire chain as a witness. That's what I was telling you. Every IoT device can afford to have the block header chain and can afford to independently verify all transactions as a wallet embedded inside the IoT device also. So that's the scalable. The design is a hyper scalable blockchain system. That's what the BSV blockchain provides. That's the only scalable terabyte size blockchain system out there that can provide a very scalable system of transactions that can achieve 100 million or more transactions per second. Right now, it has already demonstrated multiple million transactions per second with the terabyte size blocks that's created. So this entire structure that you see, the Merkle branch, the Merkle root, and how the SPV system creates peer-to-peer transactions, which can be independently verified at the edges of the network. All of this is the structure that makes the blockchain a scalable system, which is very much required. Now, with that, what we get is a huge and highly scalable blockchain infrastructure as provided by the BSV blockchain with very low cost transactions of sub-cent value per transaction fees, with instant settlements possible because your receiving wallet can independently verify it with zero confirmations required. And it has a scalability for transactions capacity, as I told you, for mass adoption. And every wallet can witness and keep the block headers and independently verify all the transactions. They don't need to keep the entire list of all transactions because, as you saw, you don't need to keep all the hashes and all the transactions that made up the hash 1 in this diagram, right? That could be pruned. You only kept the Merkle paths relevant to the transactions and the UTXOs that your wallet has. So with that, you are able to essentially scale indefinitely because this is achieving a division of labor and also validation at the edges of the network, which scales the blockchain uh, without any limits. And that's what is ideal for achieving the vision, which is very big vision of achieving the entire global economy on the one global blockchain. That requires a highly scalable blockchain capable of millions of transactions. per second for supporting even just the global digital economy, right? So that is the end of today's lecture. What we are going to do in the next lecture is creating wallets, SPV wallets particularly. You'll be having addresses created. A wallet is simply a creation of a key pair, which maintains a set of UTXOs that your key pair controls essentially to unlock those and create transactions. You would be sharing your addresses between each other and creating transactions between each other and transmitting satoshis. I'll give you some satoshis myself, then you can experience them, send them to each other, and get instant confirmation transactions of how the BSV blockchain works. And we'll be creating applications in the next workshop also. So you would get a template to create how to create an application that you can. It would be a Next.js project. If anybody of you knows Next.js, it would be good. It's the most popular framework for creating applications, full stack applications. So in this hackathon also, you would be required to create applications. So you can use that template, which will be given in the next workshop. For that workshop, you need to make sure that you need to have the Node.js environment installed on your system, as well as the Visual Studio Code environment installed on your system. Visual Studio Code is a code editor used to edit code, and Node.js is the JavaScript runtime. That's what we will be using to run the workshop template code, which would give you a template that integrates the blockchain wallets into your front end or back end applications that you build for the hackathon. That's all for today's workshop. Any questions that you have, I'm open and you can ask any questions. Thank you.
Sorry, guys, I was muted. So once more, thank you very much for this workshop. It was really, really great, and it was very interesting for the new developers. And I believe that the new developers can better understand what the blockchain is and how it works, and prepare better for the tomorrow workshop, but also for the incoming hackathon during this weekend. So thank you once more, and I see that we don't have any questions, so we can finish today. And we want to invite all of you for tomorrow for the next session. We deep dive in the SP wallet. Thank you once more.
Thank you, guys.
Thank you. Bye bye.
Bye.